Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine, just for a second, the ultimate fate of our own solar system.
Right.
Because, we always think of the sun as this permanent fixture. But in about 5 to 8 billion years, it's going to run out of fuel. It's going to shed its outer layers and shrink down into this incredibly dense, Earth-sized stellar graveyard.
Mm-hmm.
A white dwarf.
Exactly. A cooling ember in the dark.
Yeah, and it's a very quiet, solitary end. Or at least that's the picture you get in standard textbook astronomy. A peaceful, dead star just floating in absolute silence. But this is where it gets interesting. Imagine pointing a highly sensitive X-ray telescope at one of those supposedly dead, silent patches of space.
Where standard physics says there should just be absolutely nothing.
Right. Nothing.
Yeah.
But instead you were just blinded by an X-ray scream so intense, so furious, that it completely shatters that peaceful image. You're suddenly looking at an impossible engine running with zero fuel.
It is entirely paradoxical. And that exact paradox has been keeping a very specific subset of the astrophysics community awake at night for a while now.
I can imagine.
Because, like you said, we had this peaceful picture, but over the last 15 years or so, observational astronomy has completely shattered that image. We've realized the universe is vastly more chaotic, and binary or multi-star systems are actually incredibly common.
Right, they're the norm, not the exception.
A solitary star, like our sun, is actually sort of an anomaly. Most stars out there have a dance partner.
And when one of those partners reaches the end of its life and becomes a white dwarf, things get really violent.
Wow. Violently is definitely the operative word here. Because you have to remember what a white dwarf is. It has this extreme mass, like the mass of a whole sun, but it's compacted down into a tiny volume, roughly the size of the Earth.
That density is it's hard to even wrap your head around.
It is. And because of that density, its gravitational pull is immense. So if it happens to be in a close binary system with a companion star, it doesn't just sit there. It starts exerting these extreme tidal forces on its neighbor.
It's actively pulling on it.
Right. It literally snatches away or accretes the outer gaseous envelope right off that companion star. And this material doesn't just fall straight down onto the white dwarf. Because of the conservation of angular momentum, it spirals inward.
Like water going down a drain.
Exactly. And it forms what we call an accretion disk.
Okay, let's unpack this for a second, because that accretion disk is the key to that traditional X-ray signal we were talking about, right?
Yes, absolutely.
We aren't just talking about a gentle swirl of gas here. We're talking about material moving at relativistic speeds, just grinding against itself.
Precisely. The friction inside that accretion disk is just incomprehensible. As the material spirals closer and closer to the white dwarf surface, it gets superheated to millions of degrees.
Wow. Millions.
Yeah. And when plasma hits those kinds of temperatures, it naturally emits high-energy X-rays. So for observational astronomers, this created a really solid, reliable diagnostic rule.
A signature.
Right. A signature. For half a century, if your telescope picked up this brilliant, sustained X-ray signature coming from a white dwarf, you knew with absolute certainty what you were looking at.
You were watching an accretion event.
Exactly. You were watching a dead star cannibalize its neighbor. It was brutal, it was simple, and we understood the mechanics perfectly.
Which brings us back to the mystery, the impossible engine. Because what happens when you look through that same telescope and you see that exact same definitive X-ray signature tearing through the void?
But there's no companion.
Right. You look for the neighbor, and there's absolutely nothing there. It's just a solitary, hyperdense remnant screaming X-rays into the void. No accretion disk, no neighbor to feed on, just alone.
It breaks the model completely.
How does a white dwarf generate that kind of friction and heat entirely on its own?
Well, that question is the focal point of this massive paradigm shift we're currently seeing unfold. It's all stemming from some groundbreaking discovery work by researchers at the Institute of Science and Technology, Austria, or ISTA.
Yeah, led by Assistant Professor Ilaria Cayasso and her PhD students, Andre Cristea and Ayush Desai.
Exactly. And they haven't just found some weird glitch in the telescope data. They've identified two deeply bizarre, totally isolated cosmic objects that defy all the established rules of the standard accretion model.
Two of them.
Two of them. And over the course of our conversation today, we're really going to dig into the violent cosmic collisions that birth these solitary remnants and how their existence has essentially forced astronomers to officially define an entirely new class of star remnants.
Let's start with the first anomaly, because it has, honestly, one of the best nicknames in astrophysics.
It really does.
Gandalf.
Yes, Gandalf the rule breaker.
Ilaria Cayasso actually spotted this one during her postdoctoral research, right?
Yeah.
And then the incredibly detailed follow-up was recently published in Astronomy and Astrophysics.
Right, led by Andre Cristea.
So when astronomers first got a read on Gandalf, my understanding is it actually looked like a standard binary system at first glance. Like, they detected material swirling around it, so the initial thought was, okay, we have an accretion disk, there must be a companion hidden in the glare.
That was the immediate assumption, yeah. Because seeing material around an X-ray source is classic binary behavior. But that theory fell apart almost the second they measured how fast Gandalf was spinning.
Okay, let's unpack this spin rate, because it's fast, right?
It's absurdly fast. Gandalf is rotating on its axis once every 6 minutes.
6 minutes.
Yeah.
For an object the mass of the sun.
Right. And to understand why that completely destroys the binary companion theory, we have to talk about orbital synchronization.
Okay.
When you have two massive bodies orbiting really close to each other in a binary system, especially if one of them is the highly magnetic white dwarf, the tidal and magnetic forces between them create this immense drag.
Kind of like the moon and the Earth.
Very similar, yeah. Over time, those forces compel the rotation of the white dwarf to synchronize with the orbital period of its companion. They get locked together in a rhythm.
Okay, so if Gandalf is spinning every 6 minutes, and it supposedly had a companion locked in that rhythm,
that companion would have to be whipping around the white dwarf in a 6-minute orbit.
Is that even physically possible? I mean, wouldn't the stars just tear each other to shreds at those speeds?
It is physically impossible. The centrifugal forces alone would just completely shred a companion star long before it ever reached an orbit that tight.
Oh.
For some context, the absolute fastest known orbit for a binary system of this specific type is around 80 minutes.
80 minutes versus 6 minutes. That's a huge difference.
It's the cosmic speed limit. Anything faster, and the structural integrity of the companion star just completely fails. So the math gives us a hard stop. You cannot have a binary system orbiting every 6 minutes.
Therefore, Gandalf cannot have a companion.
Exactly. It is mathematically, unequivocally alone.
So if it's completely alone, what on earth is that material swirling around it? Because that initial observation wasn't wrong. There is gas there. How do astronomers actually figure out the shape of gas around a star that's, thousands of light years away?
That's where we rely on optical emission spectra. We basically look at the light.
Yeah.
Astronomers take the light coming from the immediate space around Gandalf and pass it through a spectrograph. It separates the light out into different wavelengths. And when a gas, like hydrogen, is heated and ionized, the electrons in its atoms jump to higher energy states.
And when they drop back down, they release light.
Exactly. They emit photons at very specific, predictable wavelengths. We know exactly where those hydrogen emission lines should be on the spectrum.
But the hydrogen signature around Gandalf wasn't a normal line.
No, it was deeply strange.
From what I saw in the data, it didn't show a steady emission line at all. It showed a signal that constantly alternated between two distinct peaks. And it was perfectly synchronized with Gandalf's 6-minute rotation.
That's exactly right.
The researchers literally described the shape on the readout as looking like cat ears.
Yes, the cat ear spectra.
So what does a cat ear shape in a light spectrum actually tell us about the physical space, like the geometry around the star?
What's fascinating here is how we use the Doppler effect to translate variations in light into physical geometry.
Okay, Doppler effect. Like an ambulance driving by.
Exactly like that. We all know how sound waves compress as an ambulance moves toward you, making a higher pitch, and stretch as it moves away, making a lower pitch.
Right.
The exact same kinematic principles apply to light. If glowing hydrogen gas is moving toward our telescope, the light waves get compressed. That shifts the emission line to a slightly higher frequency, which we call a blue shift.
And if it's moving away.
The waves stretch out, shifting the light to a lower frequency, a redshift.
Got it. So if you have a uniform ring of gas, like think of Saturn's rings, but made of hot plasma spinning around a star, you would constantly be seeing both shifts at the exact same time.
Right, because one side of the ring is always coming toward you, and the other side is always rotating away from you.
Okay, so that would just look like a wide, stable line on the graph.
Precisely. A continuous, uniform disk of material produces a stable, broadened emission line with two constant peaks.
But that's not what the cat ears look like.
No, it wasn't. The cat ear's signature wasn't constant at all. Those blue shift and red shift peaks alternated. They faded in and out over that exact 6-minute rotational period.
Wow.
And if you run the math and model the kinematics required to produce that highly specific alternating light signature, there's only one geometric solution.
And what is it?
You aren't looking at a continuous disk of material. You were looking at a broken, asymmetrical half ring of ionized hydrogen plasma.
A half ring.
Just suspended in space, orbiting the star.
Logically, that sounds fundamentally wrong. Gravity is a central force. It pulls equally in all directions toward the center of mass.
It does.
If you put a clump of debris in orbit around something, that massive orbital mechanics dictates that over time it's going to shear apart, spread out, and eventually form a continuous uniform disk.
Right.
Gravity abhors an asymmetrical half ring.
Gravity absolutely abhors it. If gravity were the sole force governing the architecture of that system, that half ring of plasma would destabilize and smear out into a uniform disk in a matter of hours, maybe even minutes.
Wow, really? That fast?
Oh, absolutely. The extreme gravitational shear near a white dwarf makes it physically impossible to maintain a clumped structure like that. So physics demands the presence of a second force, an overpowering force acting as a containment vessel.
And since we're dealing with ionized gas, essentially a soup of charged particles, the only force out there strong enough to grapple with charged particles against that much gravity is a magnetic field.
Exactly, magnetism. But it cannot just be a standard dipole magnetic field.
Like the Earth's magnetic field, with a north and south pole.
Right, it can't be like ours. To trap plasma asymmetrically and hold it rigidly suspended in a half ring on just one side of the star, the white dwarf has to possess a phenomenally strong, violently asymmetrical magnetic field.
Violently asymmetrical.
The magnetic flux lines have to be severely lopsided. They have to project much further and much stronger out into space on one side of the hemisphere than the other.
So it's basically acting like an invisible magnetic claw.
That's a great way to picture it. An invisible claw gripping this plasma and whipping it around the star every 6 minutes.
The idea of a lopsided magnetic claw holding a chunk of plasma is wild enough on its own. But it gets even weirder when you look at standard stellar evolution.
It really does.
Because white dwarfs at Gandalf's stage of life, under normal circumstances, shouldn't really have massive magnetic fields at all, let alone a highly lopsided one.
Right. The magnetic dynamos of typical stars tend to decay, or at least become highly uniform, as they collapse and cool into a white dwarf.
But how did Gandalf get this claw?
Well, that is the crux of the riddle. High-field magnetic white dwarfs are already exceptionally rare. But an isolated, ultra-massive white dwarf with a profoundly asymmetric magnetic field that completely defies normal cooling models.
It needs a different origin story.
Exactly. It requires an entirely different genesis. Gandalf did not evolve peacefully from a single dying star. It is what we call a merger remnant.
Meaning it's the aftermath of a cosmic car crash.
A cataclysmic one. Our best models indicate that about 60 to 70 million years ago, there were two separate white dwarfs locked in a decaying binary orbit.
Okay, so two dead stars spiraling toward each other.
Right. As they lost orbital energy, likely through the emission of gravitational waves, they spiraled inward until they finally violently collided and merged into one body.
The violence of two Earth-sized sun mass objects slamming into each other. It's almost unimaginable.
It's beyond human comprehension, really.
And I'd imagine that collision is exactly what kicked its spin rate up to 6 minutes. Just all that orbital momentum from the two stars getting crushed into a single body.
Yes, exactly. The rotational energy from that decaying orbit is conserved in the newly merged body. That results in that frantic 6-minute spin.
But what about the magnetic field?
Well, the sheer physical trauma of the impact, the turbulent mixing of the two stellar cores during the merger, that generated a chaotic, incredibly powerful magnetic dynamo. That collision is what forged the lopsided magnetic field we see today.
So we have a star born from a violent collision between two dead stars. It's spinning frantically every 6 minutes. It's holding onto a half ring of plasma with a twisted, lopsided magnetic field. And somehow it's blasting out X-rays without any companion to feed on.
It really is a list of impossibilities.
It totally earns its name. Because Andrei Christea actually named it Gandalf because, much like the wizard in Tolkien's universe, it likes to speak in riddles.
It's the perfect moniker. Every single time they point an instrument at it, the data just provides a clue that leads to a deeper, more frustrating physics problem.
But if you find one incredibly strange, rule-breaking object out in the vastness of space, the immediate question is always, is this a complete fluke?
Right. The inherent challenge with observational astronomy is always the sample size. The scientific method demands skepticism.
Did we just stumble upon the single strangest accident in the Milky Way? Or is this part of a pattern?
Is Gandalf the Rosetta Stone for an entirely unmapped branch of stellar physics?
Exactly.
Yeah.
A sample size of 1 is just an anomaly. But a sample size of 2, that's a pattern. And that pattern actually emerged when the team started digging into historical data.
Yes. Back in 2021, Ilaria Caiazzo had cataloged another highly unusual object.
And recently, a 2025 paper led by Ayush Desai took a much closer look at this second object, using advanced UV and X-ray data. And the second remnant has a much more literal name. It is simply called moon-sized.
It is a literal name, but the implications of its physical dimensions are just staggering.
Here's where it gets really interesting, because calling it moon-sized almost undersells the horror of its physics.
It does.
When we say moon-sized, we're talking about an object that contains the entire mass of our sun. A star so massive you could fit 1 million Earths inside of it. And now, take all of that mass and crush it down into a sphere with a radius roughly equivalent to our tiny moon. The density is borderline incomprehensible. You're talking about crushing 1 million Earths into a space smaller than Asia.
To put some hard physics behind that density, we actually have to talk about the structural limits of matter.
Okay, let's hear it.
In a normal star, like our sun, the inward crush of gravity is constantly balanced by the outward pressure of nuclear fusion happening in the core.
Right, an ongoing explosion pushing outward.
Exactly. But when the fusion stops, gravity wins and the star collapses. For a white dwarf to stabilize at the size of the moon while holding the mass of a sun, it relies entirely on a quantum mechanical phenomenon.
Electron degeneracy pressure.
Yes.
I've read about this, but the mechanics of it are deeply counterintuitive. It's not physical matter pushing back against gravity. It's actually a rule of quantum physics, right?
That's right. It stems directly from the Pauli exclusion principle,
Which states that no two electrons can occupy the identical quantum state at the same time.
Exactly. Think of it like a very strict set of assigned seats in a theater. As gravity crushes the matter of the star denser and denser, the electrons are stripped from their nuclei and forced into a smaller and smaller volume.
So the seats are filling up.
Right. Eventually, all the lowest energy states, the front row seats, are completely filled. If gravity tries to compress the matter even further, the electrons literally have to occupy higher and higher momentum states, simply because there's no room left for them in the lower states.
They refuse to share a seat.
Exactly. This quantum resistance to being squeezed into the same state creates an immense outward pressure. That quantum resistance is literally the only thing preventing moon size from collapsing entirely into a neutron star or even a black hole.
It's existing right on the razor's edge of physical collapse.
It is pushing the absolute limits of what matter can endure.
So we have this incredibly dense, volatile object. And the ICER researchers quickly realized that moon-sized is essentially Gandalf's twin, just at a very different point in its life cycle.
Precisely. They are fundamentally the exact same type of object. Both are isolated, ultra-massive, highly magnetic merger remnants.
But the timeline is the key differentiator here.
Yes. We estimate that the violent collision that birthed Gandalf happened roughly 60 to 70 million years ago.
Which, in galactic terms, is basically yesterday.
It is incredibly recent. Gandalf is essentially a fresh wound. But moon-sized, on the other hand, is an ancient scar. Its merger event is estimated to have occurred roughly 500 million years ago.
500 million years of evolution between the two.
Right.
That age gap has to account for some major differences in how they look and behave today, right?
It accounts for almost all of the observational differences. Because moon size has had 500 million years to cool down, settle, and interact with its surrounding environment, it lacks all the chaotic debris we see around Gandalf.
So there's no half ring of plasma.
No half ring, there are no cat-ears in its optical spectrum. Whatever shrapnel or material was suspended around it in the millions of years right after its merger, it's gone. It's either been fully consumed, ejected out into deep space, or it's cooled into invisibility.
But it's still emitting X-rays, even after 500 million years completely alone.
It is, and that is the defining link between the two. However, the X-ray emissions from moon-sized are significantly weaker.
How much weaker?
About 100 times dimmer than the blinding X-ray flux we see coming from Gandalf.
Wow, okay. So it's fading.
It heavily implies a process of decay, yes. When astronomers analyze moon size, they are basically looking at a temporal mirror. They're looking at the future of Gandalf.
Right.
Whatever mysterious engine is actually powering the X-rays in these solitary remnants, it slowly runs out of fuel or it loses momentum over a timescale of hundreds of millions of years.
So we now have two incredibly strange objects. They're separated by vast distances and hundreds of millions of years of evolutionary time, but they share an incredibly specific set of highly unusual traits.
They completely break the standard accretion model for X-ray generation.
And they don't behave like standard isolated white dwarfs either.
Yeah.
So how does the astrophysical community actually deal with objects that just refuse to fit into any of the established boxes?
Well, you have to draw a new box. You have to redraw the taxonomy. As we discussed, a single anomaly is just a curiosity.
Right.
But when you have two distinct objects at different evolutionary stages, exhibiting the exact same set of overlapping, previously unexplainable phenomena, it crosses a critical threshold in science.
It gives them the confidence to say this is real.
Exactly. It gives researchers the empirical confidence to state that they haven't just found a weird star, they've actually discovered an entirely new branch of stellar evolution.
And the ISTA team basically planted a flag here. They established 5 core pillars, 5 absolute criteria that officially define this brand new class of cosmic objects.
Yes, the 5 metrics.
Let's break down the architecture of this new class. If an anomaly hits all 5 of these, it belongs in the category.
Okay.
First pillar. They must be ultramassive.
Right. Pushing the absolute limits of electron degeneracy pressure, which strongly indicates they are the result of a violent merger rather than a single star's natural collapse.
Second pillar. They must be highly magnetic.
Possessing field strengths millions of times more powerful than Earth's, which is generated by the turbulent dynamo effect of that initial cataclysmic collision.
Third pillar. They must be rapidly rotating.
Spinning on the order of minutes, not days or hours, conserving all the angular momentum of the destroyed binary system that birthed them.
Fourth pillar. They must be completely, unequivocally companionless.
Meaning any energy they project, any X-rays they emit, cannot be explained away by the standard, comfortable physics of cannibalizing a neighboring star.
And the fifth pillar, the anchor of the whole mystery. They must be X-ray emitting.
And both Gandalf and Moonsize check every single one of those 5 boxes perfectly.
So what does this all mean? If you're listening to this and you're just a casual observer, you might look at this and say, okay, astronomers made a new folder on their computer for a couple of dead stars. Why should I care?
Right. Why does it matter?
It matters because every time a new class like this is codified, it proves that our understanding of thermodynamics, of gravity, and of energy generation is fundamentally incomplete.
It forces a rewrite of the textbooks.
Exactly. The universe is actively generating vast amounts of high-energy X-rays using a mechanism that literally doesn't exist in our textbooks. We are witnessing physics that we do not yet comprehend.
That is the perfect way to frame it, because the first law of thermodynamics is absolute. Energy cannot be created from nothing.
Right.
The X-ray luminosity coming from Gandalf and moon-sized requires a colossal expenditure of energy. If there is no accretion disk feeding material into a gravity well, what is the engine? How are these isolated cooling embers generating the millions of degrees required to emit X-rays in the first place?
That is the massive riddle Gandalf leaves us with. The new class is defined, the pillars are set, but the engine driving the whole thing remains a ghost.
A total ghost.
And to try and capture that ghost, the ISTA team had to build a theoretical framework. They laid out 3 distinct, physically plausible scenarios to try and explain where these X-rays are coming from. And then they began the brutal process of attempting to disprove their own ideas.
Which is the scientific method in its purest form. You formulate hypotheses, apply the observational data, and see which models break under the pressure. The 3 scenarios they propose fundamentally alter how we view isolated stellar bodies.
Let's dive into scenario 1. This is the outflow scenario. And from reading the research, it seems to be the personal favorite of Ayush Desai.
It is, yeah.
Because this scenario completely abandons the idea of material falling onto the star and instead looks at material being violently ejected from the star.
Correct. The outflow scenario relies entirely on the internal inherent physics of the remnant itself. We have to look at the combined effects of the second and third pillars of our new class: extreme magnetism and extreme rotation. When you take a highly conductive body like a white dwarf, give it a profoundly strong magnetic field, and then spin it at phenomenal speeds like Gandalf's 6-minute rotation, you effectively turn the entire star into a gargantuan unipolar inductor.
A unipolar inductor, that sounds like you're generating an electric current just by spinning a magnet.
That is exactly what is happening, but on a massive cosmic scale. The rotation of the magnetic field through the vacuum of space generates an electromotive force of unimaginable magnitude across the surface of the star.
Wow.
The hypothesis here is that this induced electric field is so powerful, so violent, that it overcomes the star's own massive gravity. It literally rips electrons and charged particles directly off the surface of the white dwarf and accelerates them out into space along the magnetic field lines.
So the star is basically acting like a cosmic centrifuge, spinning so fast and with such magnetic violence that it's literally flaying its own surface. It's extracting its own plasma.
Yes.
And as that plasma gets accelerated outward along those magnetic lines, the friction and the energy release blast out X-rays.
Precisely. The acceleration of those charged particles to near relativistic speeds would produce the exact high-energy emissions we observe. The reason Desai and others favor this model is its theoretical elegance.
Because it's entirely self-contained.
Exactly. It doesn't require a companion, it doesn't require leftover debris, and it doesn't rely on complex orbital mechanics. The star provides its own fuel and its own engine.
But there's a catch with this elegance, isn't there? We've seen this unipolar inductor mechanism before in space, but never in a white dwarf.
We haven't. This specific mechanism of magnetic outflow is the exact engine that powers pulsars.
Real pulsars.
But pulsars are rapidly rotating neutron stars. They are vastly more dense and possess magnetic fields magnitudes stronger than even Gandalf.
So if the outflow scenario is correct,
it means we have to rewrite stellar physics to acknowledge that white dwarfs are capable of pulsar-like behavior. We have never successfully modeled or observed this in a white dwarf before. It's a massive radical leap in our understanding of electromagnetic dynamics.
Okay, so that's the outflow model of the star ripping itself apart from the inside out. Scenario 2 takes the complete opposite approach. This is an inflow scenario, specifically focusing on leftover shrapnel.
All right.
And this model goes back to the incredibly violent origin story of these remnants.
It does. The merger of two white dwarfs is not a clean surgical process. When two sunmass objects collide, an enormous amount of matter, superheated gas, plasma, heavy elements is violently ejected from the system.
It's a cosmic explosion.
A massive explosion. The hypothesis in scenario 2 suggests that a significant portion of this blast shrapnel didn't reach escape velocity. Instead, it was thrown into highly eccentric, elongated orbits.
Meaning the debris was blasted incredibly far away from the new star, way out into the deep freeze of the surrounding system. It slows down at the furthest point of its orbit before gravity finally hooks it and pulls it back in for a long, screening fall toward the surface.
Exactly. And because those orbits are so eccentric and chaotic, the material doesn't fall back all at once. It trickles back over massive timescales. As this ancient shrapnel finally plunges back down the gravity well and smashes into the surface of the white dwarf, the kinetic energy of the impact is converted into thermal energy.
And that generates the X-rays.
Exactly.
I have to be honest, I struggle heavily with the physics of this timeline.
It is the main sticking point, yeah.
I can buy this for Gandalf. Gandalf's merger happened 60 to 70 million years ago. Sure, maybe you have eccentric orbits that take tens of millions of years to complete a single revolution.
Right.
But moon-sized is 500 million years old.
Yeah.
500 million years. How can you have an orbit so perfectly eccentric that it takes 500 million years for debris to finally rain back down? Wouldn't orbital decay, perturbations, or just the solar wind have cleaned out that debris field millions of years ago?
Yeah.
It feels like relying on an incredibly lucky, sustained drizzle of shrapnel for an impossible amount of time.
Your skepticism is entirely justified, and it targets the fundamental weakness of the shrapnel hypothesis. Maintaining a consistent, measurable flow of material from a single, discrete, explosive event over 500 million years stretches the limits of orbital dynamics to their absolute breaking point.
It just doesn't seem mathematically sound.
The mathematics of orbital decay suggests that the vast majority of that material would either be quickly reaccreted or permanently lost to the interstellar medium long before moon-sized reached its current age.
Right.
While you can theoretically construct an orbit on paper that takes 500 million years, assuming a dense enough population of shrapnel to fuel a constant X-ray source is highly improbable.
Which naturally leads us to the final proposed engine. Scenario 3 is also an inflow model, but instead of relying on leftover shrapnel from the star's birth, it relies on what astronomers call cosmic pollution.
This scenario grounds itself in phenomena we've actually observed in thousands of other systems. Thanks to wide-field spectroscopic surveys over the last 2 decades, we know that about 1/3 of all isolated white dwarfs are actively polluted.
What exactly constitutes pollution for a dead star? We aren't talking about gas here.
No, we are talking about rocky planetary material.
Okay.
Consider the history of a white dwarf. Before the star died, it likely hosted a complex planetary system. Gas giants, rocky terrestrial worlds, asteroid belts, comets.
Like our solar system.
Exactly. When the star expands into a red giant before collapsing into a white dwarf, the gravitational dynamics of the entire system are thrown into absolute chaos. Planets migrate, orbits cross, and asteroid belts are completely destabilized.
It's a gravitational mess.
It really is.
Yeah.
For hundreds of millions of years after the star becomes a white dwarf, stray asteroids or even entire displaced planets can wander too close. The immense tidal forces of the white dwarf will literally shred these rocky bodies into dust, which then rains down onto the surface.
And when millions of tons of pulverized planetary rock hit the surface of an ultra-dense white dwarf, that impact generates extreme heat, and heat creates X-rays.
Precisely. And the great thing is, because we can read the optical spectra of these stars, we can actually see the chemical fingerprints of the shredded planets.
Oh.
A pure white dwarf should only show hydrogen or helium in its atmosphere. When we see heavy elements, carbon, silicon, iron, magnesium, we know the star is actively consuming rocky debris.
And this scenario looked incredibly promising at first, right?
Yeah.
Because when the ISTA team looked at Gandalf's optical spectrum, they didn't just see the weird hydrogen cat ears.
No, they didn't.
They saw heavy metals. They found distinct signatures of carbon and silicon-rich materials polluting the atmosphere.
They did. The data clearly shows that Gandalf is currently actively accreting rocky planetary debris. The chemical signature is undeniable. So initially, Scenario 3 seemed like the perfect, elegant solution. Gandalf's X-rays are being powered by the tidal disruption and consumption of a surviving planetary system.
But science requires consistency. If you claim to have found the engine for a new class of objects, that engine has to work for every member of the class.
If we connect this to the bigger picture, this raises an important question, and it is the exact hurdle that Scenario 3 stumbled over. A valid hypothesis must be universal within the defined parameters.
Right.
When Desai and the research team applied the exact same spectroscopic analysis to the older twin, moon-sized, the results were completely contradictory.
What did they find?
They found absolutely zero trace of carbon, silicon, or any heavy element pollution. Moon-sized's atmosphere is completely clean.
So whatever is generating the X-rays in moon-sized, it definitively is not the consumption of rocky planetary debris.
Exactly. And because the fundamental requirement of this research is to identify the singular mechanism defining this new stellar class, Scenario 3 fails the test.
It falls apart.
While cosmic pollution might be happening at Gandalf, it cannot be the foundational mechanism responsible for the X-ray emissions in both objects. Therefore, through the rigorous application of the scientific method, the ISTA team has relegated the pollution hypothesis to the least likely explanation for the class as a whole.
So we are left with a phenomenal astronomical cliffhanger.
We really are.
We have a masterfully defined new class of stars, anchored by 5 undeniable physical pillars. But the engine driving their most violent and defining feature remains completely shrouded in mystery. The outflow model forces us to accept pulsar physics in a white dwarf. The shrapnel model stretches orbital mechanics to the breaking point. And the pollution model completely contradicts the observational data of the older twin.
That is the leading edge of astrophysics. We have deduced the shape of the puzzle, but we are missing the central pieces.
Let's take a macro view of the journey we've mapped out here today. We started by dismantling the comforting idea that stars like our sun die quietly.
Right.
We dove into the violent, cataclysmic reality of stellar mergers. We've had Gandalf, a deeply scarred, ultra-massive remnant spinning frantically every 6 minutes, defying the central force of gravity by gripping a half-ring of plasma within an impossible, lopsided magnetic claw.
Such a wild object.
And then we extrapolated 500 million years into the future to meet moon-sized, an ancient twin crushing the mass of our entire solar system into a sphere barely larger than the rock orbiting our own Earth, its X-ray scream slowly fading into the dark. We watched these two cosmic anomalies forcefully dismantle the traditional accretion model and compel the scientific community to invent an entirely new taxonomic category for the cosmos.
It is a staggering narrative of discovery.
Yeah.
But the work is really only just beginning. The immediate, vital mission for the ISTA team and truly for X-ray observatories globally is to expand the catalog. We need to find the third, the fourth, the 10th member of this isolated magnetic class.
Because right now you're trying to plot a complex evolutionary graph with only 2 data points.
Precisely. 2 data points give you a line, but they don't give you the full curve of evolution. If we can locate more of these remnants at different ages, say one that is 50 million years old and another that is 2 billion years old, we can map the decay rate of their X-ray emissions and their magnetic fields.
That makes sense.
More data will allow us to confidently eliminate the flawed hypotheses, or, perhaps more thrillingly, the new data might reveal a completely unexpected, entirely unhypothesized branch of physics that resolves the paradox.
That is the beauty of this kind of research. It never really ends. It just upgrades the quality of the questions we're allowed to ask.
Absolutely.
But before we finish up today, I want to leave you with one final, deeply unsettling thought to mull over. We've spent this entire time dissecting the physics of the stars themselves. These ultra-dense, hypermagnetic engines blasting radiation into the void.
Right.
But we briefly touched on the idea of planetary systems. Think about what happened to the worlds orbiting the original 2 stars before they spiraled into that cataclysmic merger.
Oh, wow.
Imagine, just for a moment, a planetary system that somehow manages to physically survive the orbital chaos of a stellar collision. The skies above them literally explode as their 2 suns merge into a single, hyperdense, spinning terror.
It would be apocalyptic.
And then, for the next 500 million years, those surviving planets don't get peace. They are bathed in relentless, scorching X-ray radiation. They are subjected to the violent shifting forces of a lopsided magnetic field that whips through their atmospheres every 6 minutes. They spend eons watching their newly formed sun slowly consume the pulverized remains of their neighboring planets.
That is a terrifying environment.
What kind of bizarre, heavily irradiated extreme worlds might be orbiting Gandalf and moon-sized right now, entirely hidden from our optical telescopes? What kind of unimaginable geology or even twisted radiation-hardened chemistry is being baked into existence on the surface of those planets?
It's fascinating to think about.
It's a sobering reminder that every time we discover a new violent type of star, we also have to imagine the terrifying new types of worlds that might be trapped in its gravitational grip. Keep that in mind the next time you look up at a quiet night sky.